The first one here on our list is HCN. This is called hydrocyanic acid, and we want to determine the Lewis structure of hydrocyanic acid, HCN. Okay, so HCN. All right, so what is carbon happy at?
4.
Okay, what is nitrogen happy at? 5. What is hydrogen happy at? Okay, so we need to get 10 valence electrons around HCN. Okay, what is our central atom?
Carbon.
Carbon loves 4. Okay, absolutely loves 4, so how will it get to 4? Okay, we're going to do a single bond to hydrogen, and then how will it get to 4 then? A triple to the nitrogen. Okay, so count with me the electrons. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Where will 9 and 10 go? This will have 2 lone pairs on the nitrogen. Okay, we'll do formal charge and octet rule. Okay, hydrogen 1. What is hydrogen happy at? 1. What's 1 minus 1? Okay, formal charge on that hydrogen 0. Octet rule for hydrogen 1, 2. Is that okay? Is this all right? Yes, it's all right. Okay, carbon, octet rule. Okay, octet rule, formal charge. Octet rule 1, 2, 3, 4, 5, 6, 7, 8. Good. Okay, formal charge. Ready? Count with me. Carbon 1, 2, 3, 4. What is carbon happy at? 4. What's 4 minus 4? Formal charge on that carbon 0. Nitrogen, octet rule. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8. Is that octet rule satisfied for nitrogen? Yes. Okay. Formal charge. Okay, ready? 1, 2, 3, 4, 5. What is nitrogen happy at? What's nitrogen happy at? 5. What's 5 minus 5? Okay, we got our 10 electrons. Formal charge minimized, and everything satisfies the octet rule. The octet rule for hydrogen is 2. So, okay, and this is what it would look like. Okay, how will we draw this? You know how to do a triple bond?
Yeah.
You're going to do a single bond with the hydrogen, and then
It's 3 for
yes, yeah. So you'll take a carbon. Okay, if you have it, okay, these are the triple bonds. Okay. Okay, my set is a little bit better than your set, so come on. Okay, carbon is going to be black. Okay, you're going to use these long, I don't know how you call them. Okay, long sticks, not the short one, the longer one. All right, you can see Hope also drew it. Carbon, nitrogen is blue. Nitrogen is blue. Okay. If you don't have one, that's okay, because like I said before, people in the previous years have messed it up. Oh, come on. Okay, C triple bond N. Okay, I'm going to make my triple bond here. Man, this is tight. Squeeze it. Okay, and then out of this carbon comes the hydrogen. Hydrogen is white. If you don't have it, just watch me. Okay? And what shape does this look to you? What does it look like to you? Tetrahedral? Trigonal planar? What does it look like? Linear? Okay, this is linear. Okay? All right, central atom. Okay, how many bonds and how many lone pairs? Not 4 bonds. There's 1 bond here, and the triple bond here is 2. So how many bonds and how many lone pairs? 2 bonds and 0 lone pairs. So get that sheet out. What's 2 bonds and 0 lone pairs? Okay, 2 bonds and 0 lone pairs. If you have my class, you can use table 10.1. But 2 bonds and 0 lone pairs is linear. If there's no lone pairs, you don't have to worry. Okay, so there's no lone pairs. So don't worry. Okay, it's linear. All right, how will we draw a linear molecule? Just like this. Is there anything 3D to this? Is there anything coming out towards you? Is there anything going below you? No, this is a straight line. So this is the same thing in 3D. Okay? In fact, there's nothing 3D about it. And you can actually put a lone pair here if you'd like. Okay. So we use dash and wedge bonds if it were 3D, but there's nothing 3D about a linear molecule. What's the bond angle for this? 180 degrees. Okay. So what is the hybridization for something that is 2 bonds and 0 lone pairs? Okay. We're going to take one from S and then one from P. This is an sp hybridized carbon. This is an sp hybridized carbon. Okay, we take one from S and then one from P. All right, finally, is this polar or nonpolar? Okay, we have that lone pair of electrons. What do you think it's doing? What will it do? Is this polar or nonpolar, Emily? Okay. That lone pair of electrons is pulling. The nitrogen is pretty electronegative. So is there anything pulling the outer side? Counter?
No.
So it would be polar or nonpolar? Polar. This is a polar molecule. Okay. So that's pretty straightforward. HCN. This is called hydrocyanic acid. All right, we're going to do the second one now. Okay, the second one here is BCl3, boron trichloride. Boron trichloride. Okay. I do not know if you guys have that.
We don't, but I just need.
Yeah, you need something with 3 holes. I don't think that one has boron. You may not have it for this one.
The yellow ones have 3 holes.
Okay, the yellow ones have 3 holes. The other ones have 3 holes, and then single bond with chlorine. Okay. So what is boron happy at?
No, I lied. The yellow ones.
What's boron happy at? Okay, boron is happy at 3. What is chlorine happy at? Chlorine, the halogens. What are they happy at?
7.
Okay, we have 3 of them. 21. All right, so what is our central atom? And what is attached to the boron? Cl, Cl, and Cl. What did we say about halogens? Single bond and how many lone pairs? How many? Single bond with 3 lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, 24 total valence electrons. Okay, so BCl3. All right, how many bonding and how many lone pairs for this one? How many bonds, how many lone pairs? Central atom. 3 bonds, 0 lone pairs. What's 3 bonds and 0 lone pairs? Okay, so there are no lone pairs on the central atom, so whatever the molecular geometry would be, it would be the same as the electron pair geometry. So what's 3 bonds and 0 lone pairs? Trigonal planar, okay? Okay, so let me see here. I'm going to see 3. Three bonds, and so this one that I have, you may not have it. This one seems to have 3, so I'm going to put a single bond here. I'll put a single bond here. You may not have one that has 3 holes in it, so single bond here. And chlorine is this here. Okay, this is boron, which has 3 holes, and this is the chlorine. Okay, trigonal planar. Okay, trigonal planar. So how will we draw this? Okay, we're going to draw it like this. By the way, you see the word planar here? Is there anything coming up or below, above the plane or below the plane? Planar. So we're going to draw it like this. B. Again, you may not have it because if you don't have it or you don't see it, just realize 3 bonds and 0 lone pairs is this. Okay? And what is the hybridization for 3 bonds and 0 lone pairs? How will we get to 3 and 0? We'll take 1 from S, and then how many from P? This is an sp2 hybridized boron. Okay, so sp2 is associated with what geometry? sp2 is associated with trigonal planar. What molecule did we study today, this morning? That was also trigonal planar. Formaldehyde. Remember formaldehyde? Okay. Huh? That was square planar. Yeah. Okay, formaldehyde. Those of you that came to class today, formaldehyde was also trigonal planar. Remember? Okay. Okay, is this polar or non-polar? Okay. Just keep it there. Okay, is this polar or non-polar? Just keep it there. Okay, this pulls this way. This pulls that way. This pulls that way. What's the sum of this pull and that pull? The sum is down. So is this going to be polar or non-polar? This is going to be non-polar. Okay, because the sum of this vector and that vector, that sum is pointing downwards, which cancels out the upwards. Okay, the sum is then the green. The sum of this red, I'll call it 1, and this red vector, call it 2. The sum is pointing downwards when you sum up vectors, which cancels out the upward of this chlorine. So this green cancels that red, and you guys are correct, this is nonpolar. Okay, trigonal planar. All right, ready to go to the next one, number 3, okay? 8 more to go. So this one, Hope, is a black one and 4. Yeah, 1 black and 4 of the greens.
Which one?
This one, SiCl4. Okay, SiCl4, okay? SiCl4. What is silicon happy at? What is silicon happy at? It's below carbon, and we know carbon loves this number. Okay, and what is chlorine happy at? Okay, so 7 times 4 is 28. So we have to get 32 valence electrons around SiCl4, silicon tetrachloride. Okay, what is our central atom? And what is attached to the silicon? 4 chlorines. What did we say about chlorine and other halogens? Okay, how are they going to bond? Single bond and 3 lone pairs. Okay, this is silicon tetrachloride. Okay. All right, we're going to find something that has 4 holes, which is the black carbon, and then we'll do a single bond with something that's green or something that's white. Okay, but Hope has it there. So, okay, so single bond. This is the tetrahedral carbon. Single bond. If you guys have it, if not, just follow me. Okay, just watch me or watch this. And then chlorine, I believe, is, according to my kit, orange. Can you make it, Emily? Are you able to? Carbon, 4 single bonds. There you go. Beautiful, beautiful tetrahedral. Okay? Okay, how will we draw this in 3 dimensions? Okay. Wedge and dash, good. Okay. So this one is on the plane, this one is on the plane. What about this one? What type of bond would this be? Wedge. What about the one here? Dash. Okay, there's one coming behind you, behind my palm. Pretend my palm is a plane or a piece of paper. That 4th one is coming beneath me, so that's a dash. This one coming towards you is what? Wedge. And what about this one? It's lying on the plane, and this one is lying on the plane. Okay, so it's 109.5 degrees is the perfect tetrahedral bond angle. So let's draw this here. Okay, I'm going to draw a silicon. Okay, I have 1 Cl. Okay, I have 1 Cl. Okay, if you know, a tetrahedron is 109.5 degrees. Okay, what about this one here? What type of bond? Wedge. Very good. Okay. Okay, what about the fourth one? Just a little dash. Okay. And if you're really good, which I'm not, unfortunately, you should be able to see the tetrahedron. If you're really good, you take the center of each atom. Take the center of each atom and draw a line. Does that look like a tetrahedron to you? Tetrahedron? Okay, does that kind of look like this? So we're trying to take something on a flat piece of paper and draw it in 3 dimensions. Okay. All right, how many bonds and how many lone pairs? Central atom? 4 bonds and how many lone pairs? Okay, what's 4 bonds and 0 lone pairs? Okay, so do we worry about the electron pair geometry? Okay, 4 bonds, 0 lone pairs. These two will be the same, and what is that geometry? 4 bonds, 0 lone pairs. This is tetrahedral. Tetrahedral. And 4 bonds, 0 lone pairs. What is the hybridization? How will we get to 4? We take 1 from S. And how many from P? This is an sp3 hybridized silicon. Okay, finally, is this polar or nonpolar? Polar or nonpolar? Okay, nonpolar is the right answer. This Cl cancels out that Cl, and that Cl cancels out that Cl. They all cancel each other. The poles of the electronegative chlorines cancel each other out. So this is nonpolar. Okay. All right, next one is pH3. pH3, do we have something that has 5 pairs? Yep, that's it.
Yes, the purple one is
Okay, yeah. pH3. So what is phosphorus happy at? 5. What is hydrogen happy at? How many do we have? 3. So we need to get 8 valence electrons around pH3. Okay, so what's our central atom? Okay, phosphorus. And then what does hydrogen like? Can hydrogen do double bonds? Hydrogen is only a single bond entity. Okay, 1, 2, 3, 4, 5, 6. Where will 7 and 8 go? Okay, so we have a lone pair on the phosphorus. Let's do a formal charge on this phosphorus. Count with me. 1, 2, 3, 4, 5. What is phosphorus happy at? What is phosphorus happy at? 5. Very good. What's 5 minus 5? 0. Okay. And then octet 1, 2, 3, 4, 5, 6, 7, 8. The octet rule is satisfied. All right. How many bonds and how many lone pairs for this one? How many bonds? 3 bonds. 1 lone pair. So what's 3 bonds and 1 lone pair? Okay, 3 bonds, 1 lone pair. What is the shape? Trigonal pyramidal. Okay. What's the electron pair geometry? Tetrahedral. Okay. So the electron pair geometry is tetrahedral. But why isn't the actual molecular geometry tetrahedral? Because of the lone pair. So what you can do is you can take a tetrahedral and then remove that atom and replace it with a lone pair. You replace it with a lone pair. That little lobe is the lone pair. So putting the lone pair really messes up the geometry. What was once tetrahedral, we remove that atom, the atom has come off, and now this atom has a lone pair. So now it's not tetrahedral. What will it be? Right. Because we replaced this with a lone pair, we took away the atom, we have a lone pair. This is trigonal pyramidal. That's the molecular geometry. The main theme here is that anytime you have a lone pair, that's going to distort. It's going to distort the structure, the three-dimensional structure. And there you go. Good job. Trigonal pyramidal. How are we going to draw something that's trigonal pyramidal? So I am not going to really give you a hard time on the test, but maybe I see this going, I don't know. How about we do this? I'll have this lone pair come up here. I'll have this be, this is P for P. I'll have this maybe, I don't know, come up here. I'll have this here as a wedge. I'll have this here come out, something like that. I'm not going to test you so rigidly on the exam for your dash and wedge. I just want you to get a 3D on a 1D piece of paper, So something like this. What's the bond angle here? Will it be 109.5 like the one above? Or will it be less than 109.5? It will be less, because the lone pair messes the bond angles up. All right, 3 bonds, 1 lone pair. What type of hybridization is this? How will we get to 3 and 1? It's the same, sp3. One of those lone pairs are going to reside in a p orbital. So 3 plus 1 is 4. 1 plus 3 is 4. Same thing with the one above. So this is an sp3 hybridized phosphorus. Is this polar or non-polar? The molecule is asymmetric. The molecule has this lone pair that's going to distort the structure. The electron pair is negatively charged. So yeah, this is polar. All right, 4 down, 6 more to go. What's the next one? SO4 minus 2. SO4 minus 2. Sulfate ion. And for this one, I am going to... There'll be a double bond, 2 double bonds. All right, what is sulfur happy at? 6. What is oxygen happy at? 6. What does the minus 2 mean? It gains 2 electrons, so we need to get 32 valence electrons across SO4 minus 2. This is called the sulfate ion. It was in our flashcards way back in week 1. Okay, so I'm going to use this piece of paper here because I want to show you something about the sulfate. Okay? So how are we going to do this? Okay, if you remember in lecture, how can we get a minus on an oxygen? How do we get a minus on an oxygen? Not only one minus, but we need two minus. So how will we get a minus oxygen, minus formal charge? Say that again.
Two bonds with an and then it's 6 electrons with 1 extra. I'm not gonna say it.
Okay, how will we get a negative formal charge on an oxygen? Remember from class? One bond. And how many lone pairs?
Two.
How many?
Two.
Okay, there's two ways I want you to know oxygen can bind. Okay, this way. Okay, and what's the other way? What's the other way we talked about this morning? And how many on that double bond? Okay. So use this in your toolkit. Okay, oxygen here with a single bond. Forget about the R. Focus on the oxygen. Okay, 1, 2, 3, 4, 5, 6, 7. What is oxygen happy at? What is oxygen happy at? 6. What's 6 minus 7? Okay, there's that negative 1. Okay. And does this have an octet? 1, 2, 3, 4, 5, 6, 7, 8. Good. How about oxygen in this configuration? Okay, let's do the formal charge. 1, 2, 3, 4, 5, 6. What is oxygen happy at? What's 6 minus 6? 0. Okay, let's do the octet rule. 1, 2, 3, 4, 5, 6, 7, 8. Octet rule. Satisfied. That's good. Okay, so this and this. This is how oxygen can bind. Having said that, how will we get to minus 2 now? 2 double bonds to oxygen. And then what's next? 2 single bonds. And what will be the charge on those 2 single bonds? Negative. And this is our minus 2. All right, let's see. We need 32 electrons, right? 32 valence electrons. All right, 1, 2, 3, 4, 5, 6, 7, 8. Count with me. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Remember, double bond oxygen has 2 lone pairs, single bond oxygen 3 lone pairs, but what's the formal charge on that single bond oxygen? Minus 1. Okay, so there's your minus 2, and there's your minus 2. Yes. Is this right? It is, but do you think anything else? You see anything else here? So notice my double bonds, okay? I just arbitrarily put them up and left, right? That was just random on me. Okay, what else, or where else can they go? They can go, maybe I can take this double bond and move it here. Okay, so that's one equivalent structure. So what did we call this phenomena? Resonance. Good job. Okay, so now my negative charges are here and here. You guys see anything else? Okay, where else can this double bond go? Okay, down. I'll move this pair of electrons here. Kick this one out. So now I have it, the double bond down. You guys see anything else? Where else? I have the double bond here, here, here. What else can I do it? I can do it this way, can I? Okay. I can move this pair of electrons here, move this pair of electrons there. Okay, so here, 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 here. Okay, no, I already did there. Here. Okay, so anyways, this is an example of resonance. Oops. So check out my double bonds, okay? Okay, and check out my formal charges, okay? My formal charges are delocalized. They're delocalized. They're shared between these two oxygens, these two oxygens, these two oxygens, these two oxygens. They can be essentially shared across all four oxygens. Okay, this makes them very, very stable. Okay, can you think of any other resonance structures? Okay, I have the double. Okay, I have the double bond here and here. I have it here and here. Okay, I have it here and here. Okay, I have it here and here. Okay, and I think I can do up and down. Okay, so anyways, there's about 4 resonance structures here. Okay, this is called delocalization. Okay. And this is also called resonance. Resonance. Okay, so on the exam, okay, carbonate, phosphate, sulfate, okay, all of these are resonance structures. Nitrate, okay, they have exceptional stability. It's easy for me to say. They have exceptional stability because the formal charges are equally shared across and equally dispersed across all 4 of the outer atoms. Okay, this gives resonance stabilized structures tremendous stability. That's why sulfate, nitrate, carbonate, phosphate, we know phosphate in our cells, are very, very stable. Okay, so let's get back to this. So I'll just draw it like this because of the resonance. Okay, all this is saying is that there's a resonance stabilized, and that -2 charge is stabilized across all 4 oxygen atoms. Okay? All right. This in your textbook is basically the depiction of this. Okay, all the -2 charges are equally dispersed, and all the double bonds are equally dispersed. All right. So we have a special case of resonance here. All right. I'll scan a copy of these notes when I'm finished, along with the recording. So in case you did not get this, you'll have it on Canvas by the end of today or tomorrow. Okay. So in case you didn't get this, I'll put them up on the Canvas for the lab. Okay, so this actually goes here, but anyways. Bless you. All right. What is the central atom hybridization? How many bonds? How many lone pairs? 4 bonds, 0 lone pairs. Okay. 4 bonds, 0 lone pairs. And what was 4 bonds, 0 lone pairs? Okay, tetrahedral. 0 lone pairs means that they are one and the same, the electron pair and the molecular geometry. And is this polar or nonpolar? The answer is nonpolar. Okay. First of all of these are delocalized. Second, all these oxygen poles cancel out each other. Okay, all these oxygen poles cancel out each other. Even though this is one-dimensional, all the poles cancel out. So this would be nonpolar. Another way you can see if it's nonpolar, look for symmetry. Okay, look for symmetry. Oxygen, 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 oxygen. This pulls, that cancel. That pole cancels. Okay, so you want to look for symmetry in the molecule. That's also a dead ringer for something that's nonpolar. All right, this took a little extra time because of resonance, but now we'll go to our next one here. So we're halfway through. ASF5. I don't know what AS. What is AS? Where's that? ASF5. Where's AS? I can't see.
That's arsenic. Yeah, it's arsenic.
But where is it? What group?
It's 33 under phosphorus.
Under phosphorus?
Yeah, I think group 15.
Okay,
Yeah.
so under phosphorus. So what is AS happy at? That's sulfate, yeah.
Yeah.
What is AS happy at? 5, because it's under nitrogen and phosphorus. Very good. Okay, what's fluorine happy at? 7. Yes, fluorine is happy at 7. Okay, so what will this be? AS, arsenic, and how many fluorines? 5. What do we know about halogens? How do I want you to draw the halogens? Single bond, and how many lone pairs? I want you to draw the halogens as single bonds, 3 lone pairs. Okay, no double bonds on the halogens, because that will mess up the formal charge. All right. So 40 electrons. Okay, so this should be 40 electrons. I'll let you guys count that. Okay. Okay, how many bonds and how many lone pairs? Five bonds, 0 lone pairs. What's 5 bonds and 0 lone pairs? 5 bonds and 0 lone pairs. Okay, what's 5 and 0? Where's my sheet? 5 and 0. Okay, 5 and 0 should be trigonal bipyramidal. 5 bonds, 0 lone pairs. Am I right? 5 bonds, 0 lone pairs. Trigonal bipyramidal. Okay. Okay, what's the central atom hybridization? How am I going to get to 5? sp3. sp3d. This is an sp3d hybridized arsenic, As. Okay, this is an sp3 hybridized sulfur. Okay, the one above. Okay, so we need something with 5 holes. I have something with 5. No, with 5. Okay, 1, 2, 3, 4. Okay, so we're going to find something with 5 holes for you guys. All right, I found something with 5 holes here, so we'll go ahead and do that quickly. Okay, 1, 2, 3, 4. Oh no, this has 4 holes. Trying to find an atom here that has 5 holes in it, but if not, then that's okay. Okay, here I go. 2, 3, 4, 5. Okay. Okay, so we're going to put a fluorine in here. So 1, 2, 3, 4. Got one more. 5. Okay. All right. So here we go. Okay. This is trigonal bipyramidal. Right. That's 5 and 0. Right. Emily, 5 and 0. Okay. Trigonal bipyramidal. All right. How are we going to draw this in 3 dimensions? Okay, imagine my palm is the plane of the paper. So how will you draw this? Okay, I'll have the AS here. Okay, I'll have the fluorine here, fluorine here, fluorine here. What about this one? Wedge. Okay, what about the one behind? Dash. Okay. That's how we would do ASF5. right. And finally, is this polar or non-polar before we go to the next one? That's correct. Very good, Savannah. Savannah? Non-polar. Okay. This is non-polar. Okay. Nice job. Okay, this pulls that way, this pulls that way, this pulls up, this diagonal, and this diagonal sums. It sums up to this down diagonal. Okay, this is the sum. So all of these arrows cancel out one another, and this is going to be, that's very good, non-polar. All right, next on our list, we've got 4 more to go. Okay, we're almost done. Bear with me. CH3Br. Okay, CH3Br. How will we draw this? Carbon with 3 hydrogens and 1 what? Bromine. Yep. So CH3Br. Okay. Halogens, how do I want you to draw the halogens? Single bond with how many lone pairs? Single bond with 3 lone pairs, okay? So what shape is this? Carbon with 4 bonds. 4 bonds, 0 lone pairs. Tetrahedral, that's correct, okay? Okay, nice bond angle of 109.5 degrees. And what's the central atom hybridization? How will we get to 4 bonds and 0 lone pairs? This is an sp3 hybridized carbon. Okay, so there are no lone pairs, so we do not worry about electron pair geometry. It's the same as the molecular geometry, and they're both tetrahedral because there are no lone pairs. Is this polar or non-polar? This is polar. Okay, polar. Okay, the Br is pulling. Okay, it's electronegative and it's pulling. Yes, the correct answer is that this is polar. All right, next one on our list is B2H4. B2H4. Okay, what is boron happy at? Boron is happy at 3. And what is hydrogen happy at? 1. So how am I going to get 3 here? 1, 2, 3. That would be B2H4. Okay, so we're going to look for something that has 3. I don't think we have anything with 3. I don't think you guys have it. Okay, these are the borons, and then my hydrogens are here. No, this ain't it. Anyways, this is what it will look like. Okay, I'm not going to bother. All right, how many bonding and lone pair on this boron? 3 bonding, 0 lone pair. Okay, what about this boron here? The same. Okay, so we have two central atoms. So this is a what hybridized boron? How will we get to 3? Okay, so we have an sp2 hybridized boron, and then we have an sp2 hybridized boron. Okay, so that's the central atom hybridization. And what does an sp2 hybridization mean? What type of shape is sp2? Very good. It's trigonal planar. Okay, so if I were to draw a trigonal planar, bond angle is 120 degrees. It will be something like this. Okay, it's planar. Planar, so no dashes and no wedge bonds. Okay, planar and trigonal planar is nice 120 degrees bond angles. And there are no lone pairs, so we do not have to worry about the electron pair geometry, so they are both trigonal planar. And is this polar or nonpolar? Hydrogen does not pull, boron does not pull. There's no pulling whatsoever, so if there's no pull, what would it be? Okay, yeah, boron is not considered electronegative, so it's nonpolar. And then, what's our last one here? Okay, what's the next one? C2H5Br. C2H5Br. Okay. Okay, how will we draw C2H5Br? Okay, what will carbon bond form a bond with? Well, carbon loves 4, so how will carbon get to 4? Okay, form a bond with carbon, and then what? This is one type of isomer. Okay, what about the hydrogens? 1, 2, 3. Where would 4 and 5 go? 4 and 5, and what can be found here? The bromine. Okay, bromine. Okay, so that's one way to put it. Okay. All right. So, how many central atoms are there? 2. And what is this one? What type of hybridization is this? It's the same as this one. 4 bonds, 0 lone pair. So what hybridization is that? And what about this one? sp3. Okay, so these are 2 tetrahedrals coming together. I think Hope made it. So let's go ahead and make that. I think you guys should be able to make it with what you have there. You're going to take 2 carbons and make a single bond with them. Okay, on one of the carbons, you'll fill it up with hydrogens. Okay, this is one isomer. There's more than one way to make this. Okay, the black is the carbons. White is the hydrogens. Okay, so I got my CH3, and then I'll fill the rest with hydrogens and bromines. Okay, by the way, these are the single bonds. Okay, Justin, these are the single bonds. Okay, these are going to be double bonds when you join them together. Okay, so this is a double bond. Okay, that's a single bond. I need one more hydrogen.
You need the hydrogen?
I got it. More hydrogen here. Okay, that's good. Nice job. Okay, here we go. Okay, CH3Br. Okay, so this is two tetrahedrals coming together, two tetrahedrons. Okay. You see this? Okay, this is a tetrahedral carbon. This is a tetrahedral carbon. All right, let's quickly draw that here. Okay, we're going to draw two tetrahedrals together. We'll have this one come out towards you guys. Have this come out here as the Br back, and then there's a hydrogen coming out back here. Oh, hydrogen back here. Okay. Okay. So hydrogen, hydrogen on the plane. These two coming out towards you. This is coming back, so that's dash, and then this is coming out back. That's dash. Okay, so something along the lines of this. Okay. Okay, again, I'm not going to really grill you on this dash and wedge, but the idea is that you want to depict something three-dimensional on a 1D plane. Let me draw this again here. I'm not happy with how I drew it. Maybe that's a little bit better than what I drew up above. All right, so we have two sp3 carbons here. Okay, we got two sp3 hybridized carbons. Okay, the electron pair geometry is the same as the molecular geometry because there are no lone pairs, and that is tetrahedral. And is this polar or nonpolar? Is this polar or nonpolar? The bromines, what will the bromines do? Okay, they're going to pull. Okay, the electronegative halogen, the bromine, will make this polar. Okay. All right, finally we have our last one here. So notice these are two tetrahedrons. Tetrahedral carbon joining with another tetrahedral carbon. Two sp3 hybridized carbons. And the last one is SF4. Okay, let's knock this one out. SF4. Okay, what is sulfur happy at? 6. What's fluorine happy at? 7. So 6 plus 28. Okay, we need to get 32 valence electrons around SF4. So what's our central atom going to be? Sulfur, and then we'll have 4 fluorines. Okay, what did I tell you about fluorines? How do I want you to draw them? Single bond with how many lone pairs? Single bond with 3 lone pairs. Okay, I want you to do that for all the halogens. Single bond, 3 lone pairs. Okay, let's count our electrons here. Okay, we need 34. Just want to make sure we got our 34 counted for. All right, you can count with me. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Uh-oh. 32. Where will 33 and 34 go? On that central sulfur. Okay? On that central sulfur. Okay?
It's like this. I don't have one with 5.
Yeah. Yep, that's right. All right, so how many bonds and how many lone pairs? 4 bonds and 2 lone pairs. Okay? Wait, 4 bonds and how many lone pairs? 1. Okay, so what's 4 bonds and 1 lone pair? Okay, the lone pair messes everything up. Okay, we have 4 bonds, 1 lone pair. It's not trigonal bipyramidal. Okay, that's what would happen if we did not have the lone pair. This is 4 bonds, a seesaw or distorted tetrahedron. Seesaw. Okay? I'll call it seesaw. Okay? All right, so we're going to take something that has 5, and then one of them will be a lone pair. 5. You can read it.
Yeah, but they don't have it.
They don't have, so I'll make it. 5, and one of them will be the lone pair. SF4. I'm just trying to find something with 5 holes. 1, 2. I got it here. All right, so you can watch along with me here. Okay, so we have 5 holes. 4 of them will be filled with fluorines, and then one of them will be filled with the lone pair. Okay, so we'll do that quickly, and then I'll let you guys go. Okay, 4 of these will be filled with fluorine, and then the other one will be filled with the lone pairs. Okay, so here's my central atom. It has 5 holes. 4 of them will be fluorine. Here's the lone pair. Okay, so you can see why they call this a seesaw. Okay, or distorted tetrahedron. Okay, this is how many bonds and how many lone pairs? 4 bonds and What's that thing I'm holding? Lone pair. Okay, so how will we draw this? Okay, pretend my palm is the plane, so I'll have this fluorine and that fluorine, and the lone pair here. Okay, what's coming out towards you? Wedge, and that's a fluorine, and what's coming out behind you? Okay, and there's your distorted tetrahedron, also known as seesaw. Okay, is this polar or nonpolar? Okay, polar or nonpolar? Okay, this pulls fluorine, this pulls fluorine, this pulls fluorine, this pulls fluorine, but what does this pull? Okay, that's an electron, right? Is this symmetric or not symmetric? Asymmetric or symmetric? It's asymmetric. The lone pair pulls indiscriminately relative to the fluorines. This would be polar. Okay, everyone see? This is not symmetric. It's asymmetric. The lone pair messes up the symmetry of the molecule. So it's polar. And finally, 4 bonds, 1 lone pair. Okay, 4 plus 1 is 5. What's the hybridization? Okay, we're going to take 1 from S. 3, P has 3. And then what do we recruit next? This is an sp3d hybridized sulfur. All right, there you have it. We did all 10 sets. C.
Do we have to do other 3 pin sets?
No, just 1.
Or?
Okay, so this is the results and data section of your lab notebook. And this is the results and data section of your lab report. Okay, so this is your results and data for your lab report. All you need to do is your pre-lab, post-lab, and your title page.
We didn't need to do all these other ones. Yeah. We only do 1 set. Well, I was, as I was rushing, moving between space.